Okay, so I want to pick up where we left off last week. We were talking about phase diagrams, something I'm sure you guys really love. And I know for some of you, it's the first time you've seen it. And for others of you, you saw it, but maybe didn't remember it, or maybe haven't seen it in quite this context. Remember, we're trying to figure out if we melt something in the mantle that's ultramafic and has garnet and olivine, why don't we end up with lava flows that have garnet and olivine? The melt is different than what the parent rock is. And that's why I'm putting up these phase diagrams to try to show what's going on there. Okay, so we're going to go through two sets of phase diagrams. We went through this one last week, and I'll go through it here quick again. So this particular phase diagram is for a feldspar. Okay, and this particular feldspar, the sites for the cations can contain sodium, right there, or it can contain calcium. And as it turns out, if you look, if it's purely sodium, you can see that its melting temperature is fairly low, around 1100 degrees. If it's all calcium, the melting temperature is up here. It's pretty high, right? Looking at 1500 degrees. So the bonds that are holding the sodium are much weaker than the bonds that are holding the calcium. So let's take a feldspar that has 50-50. Okay, half of those cation sites have sodium, half of those cation sites have calcium. All right, and let's start with a solid, which we're down here at low temperature, so we have a solid. So if we increase the temperature, eventually we're going to hit this line right there. Anybody remember what line that was? Okay, that is the solidus. That's the composition of the solid at various temperatures. Okay, so right at that point, you hit the solidus. You're going to start melting it, right? But what's going to come off as a melt? Well, you're going to break the weakest bonds, right? So you're going to end up with a liquid that starts right here at E. Okay, and you can see that at E, what's the composition of that liquid? It's mostly sodium rich, right? Albite. Now there's a few of the calcium that come off, right? But it's mostly sodium. So if you're pulling the sodium off of the crystal, what happens to the chemistry of the remaining crystal if you pull off all that sodium in the melt? It becomes more calcium rich, and it will follow this line, okay? And as it becomes more calcium rich, that's going to make your melt a little more calcium rich. So at every temperature, you can see the melt, which is on this line right here. This is the liquidus. This is the solidus. So the solidus tracks the composition of the solid. The liquidus tracks the composition of the liquid, right? Now, if you completely melt it, you end up back here at A, where you have a melt that's 50-50, right? But in the mantle, you're not melting everything, okay? You're only melting a few percent. So the point of this is that you end up initially melting the lowest temperature end member preferentially. Your melt is a little different than what you started with. You're going to break the easiest bonds first. Now, I could have started with, let's say right here, right? I could have started with a feldspar that's mostly calcium. And if I raise the temperature, raise the temperature, raise the temperature, what's my first liquid going to be? Mostly sodium rich, mostly albite. So the whole point of this is to show you that, yeah, you can take a mineral, and if you only partially melt it, you get something different than what you started. In order to get the same thing that what you started, you have to melt all of it. Okay? So that was my reason for showing you this. So solid solution, your initial melt, low temperature end members come out first. Now this is for a solid crystal. Don't forget that down in the mantle, we also have volatiles. There's water down there. There's other volatiles down there. What's the melting temperature of those light molecules? They're much lower, right? So they would have come off and become a gas before you even hit these temperatures. So your initial melt not only is different than what you're melting, but it also has lots of volatiles in it that get incorporated then into melt, and then all that rises up. So point being, again, you can start with a garnet, pyroxene, olivine, rich mantle, and if you only partially melt it, you get something that's volatile rich, 5 or 6% volatiles, and it has a different composition. So we went through this whole part here. What melts first? The sodium rich, because it has a lower melting point, because it has weaker bonds. And in order to get a 50-50 mix that you started with, you have to melt all of it, which you're not going to do. You're only going to melt a few to 10% or so. All right, any questions on that?
Melt it all?
Probably not. Got a massive amount of rock down there. You're only melting, it mentions here earlier, you're melting at the grain boundaries. So you're just melting off a little bit of that. Once you melt it, where does it go? Where does the melt go once you produce it? Where does it want to go? It wants to go up because it's a melt, slightly less dense. So it will move between all these grain boundaries and start to pool together in cracks. And it'll just keep moving up. It'll move up until when? What's driving it up? A difference in the density, right? It's less dense than the surroundings. So it's going to rise until it hits rocks that have the same density. And that actually happens most of the time. Because what happens to the density of rocks as you get closer to the surface? They're less dense, right? So at some point, that melt is likely to reach rocks that are the same density, and they'll stop. I told you a couple weeks ago, what percentage of magma actually makes it to the Earth's surface? Less than 10. Most of it stays down beneath the surface because it encounters rocks that have the same density. It's actually really unusual for the melt to be lower density all the way to the surface. Only happens in certain regions on Earth. Okay, so this example was for a solid solution mineral like a plagioclase. You could find a similar phase diagram for olivine, where you have a magnesium-rich end member and an iron-rich end member. But a lot of times what we have are two separate minerals. Let's say pyroxene and olivine mixed together. So here are a couple of phase diagrams where you have a mix of two distinct different minerals. Okay, maybe one's an olivine, maybe one's a pyroxene. Okay, so it's a rock with two different minerals in it. So if you were looking at this sample, you'd see, oh, there's some olivine, or there's some pyroxene, or there's some amphibole, whatever. Two different minerals in it, right? So let's start with this top diagram, okay? So let's start at 1, all right? At 1, we have solid mixture where maybe 60% of it is mineral Q, 40% of it is mineral P, okay? So it's mostly Q, right? Now we raise the temperature. We go from 1 to 2. We go up, 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 up. We hit the solidus. What's our first liquid? Right here. That's where your liquid is. And what's the composition of your liquid there? It looks like it's about 30% Q and roughly 70% P. It's mostly P, right? And it's going to stay there, okay? As you crank up the heat, more and more melting is going to occur, but it will sit right at that point until when?
All of the
Yeah, so at this line right here, you get a mixture of melt and solid A. This is melt and solid B. So you're going to get a little bit of B melting here, a little bit of A. Actually, it sits there until all of A melts. And then once all of A is gone, then it adds more B until you have the same composition of liquid that you started with at the beginning. So it sits there until all that A is gone. But what if you only melt a little bit, just a couple percent? What's your liquid going to be? It's going to be right there, right?
Yeah.
So it's really different than what you started at. I mean, look at this bottom one here where it's almost all Q, isn't it? So if you looked at your rock, you'd see 80% of one mineral and 20% of the other. But when you melt it, what do you get? You get something that's really different, right? And that's the whole point here, is that we are only partially melting the mantle. So whether you have solid solution or just mixtures of two minerals like you have here, your melt is always really different than what you started with. So this could be a garnet and say a plagioclase or something. You get a garnet rich melt? No, you end up with a plagioclase rich melt. So again, whole point is that your melt is different than your parent. Yeah.
Why does it go to 5? Where is it? It goes more than the 5.
It's okay. So yeah, I find these ones a little harder to read. Okay. So these two lines right here follow the liquid, right? This line follows the solid. What is your solid? Only A or only B. It's not a solid solution, it's just one or the other. So it's showing you that the composition is this, or the composition is that. So at first, most of your A comes off. That makes your remaining B rich, and at some point when all the A is done, you end up over here because you have no A left. At that point, then it will start following up there because that's all you have left. I can go through this with you a bit later. Sure. All right. I don't want to get too hung up on this because it's actually a really simple point, but I wanted to review some phase diagrams because if you haven't seen it before, you're going to see it in your petrology and some of your other classes. If you have seen it, then I think it's worth kind of taking a look at it again. Okay, so just to sort of summarize, in the mantle, we have a heterogeneous mantle. It's not made of one mineral, made of several different minerals. Some of those are solid solution minerals, some aren't. And the point is that when you partially melt it, the lowest melting point materials come off first. Mostly sodium-rich feldspars, pyroxenes, things like that. Stuff like olivine, if you remember from Bowen's reaction series, olivine is the highest temperature phase that you get in most melts. Those tend to melt last. They have the highest melting point. But you do get some of it. You saw in all these cases that you do get some of the high temperature minerals in there. It's just preferentially you get the low melting point minerals mostly. And this is probably the big takeaway from all this, is that in every case, you tend to end up with a melt that has a higher percentage of silica than your parent. So the melts are always more silica rich than the rocks that they started with. because in general, the lower silica minerals tend to have lower melting points. Remember, quartz is all silica, right? Quartz has a melting point of around 700 degrees. And as you go up to the higher melting point minerals on Bowen's reaction series, you actually get less and less silica that comes off. So you always produce melts that have higher degrees of silica than the parent. And silica is what really drives the behavior of these melts, these magmas, how they respond to gases, things like that. So point of those phase diagrams, you end up with a different composition than what you start. And the point here is that it always tends to be more silica rich than what you start with. So here's kind of some takeaways here. So if you start with an ultramafic parent, the typical material we have in the Earth's mantle, and you melt it a few percent, say 10 to 15%, you end up with a basaltic melt. And we have lots of basalt on Earth. Lots of basalt in the solar system. Covers Venus, covers Mars. It's all over the moon. Pretty much every planetary body in the inner solar system is primarily made of basalt. And that's the melt that you get when you partially melt an olivine, pyroxene, garnet-rich material. But here on Earth, we have other rocks that can get melted as well. If you go to subduction zone areas where you have ocean crust that's being subducted into the mantle, and you partially melt that material, you end up with something that's more silica rich. In this case, you end up with an andesite. What do we have at lots of subduction zones? We have lots of andesite, because you're actually melting a different starting material. You're melting a lot of that ocean crust that's getting subducted. Where you have mid-ocean ridges and oceanic hotspots where the mantle's really close to the surface, that's where your ultramafic stuff is close to the surface. It gets melted into basalt. That material from the ridges spreads out over time, eventually gets subducted along continental margins. That material can then melt, and it forms andesite. And then if you have truly continental areas, they're made of stuff like andesite, and melt that, you end up with something that's even more silica rich. So silica rich that quartz will actually form in it. You end up with rhyolites. Again, leading back to all that material we talked about with the phase diagrams always giving you a different melt than your starting composition, and it's always more silicic. So these last couple of slides are really what I want you to focus on. For partially melting material, you end up with a different melt than the rock you started with, and that melt is always more silicic rich than the rock you started with. So go to the different areas on Earth where you have volcanism. You go out into the oceans. The parent rock there is your ultramafic mantle. You end up with basalts that form as the melts. Go to subduction zones where you're subducting ocean crust. That stuff melts, gives you andesites that come out of very explosive volcanoes. And then if you have a place like Yellowstone, truly continental, you start with continental rock material like andesite and some other rocks as well. You melt that, you end up with a really silica-rich rhyolite. So basalts, just for your recollection, are somewhere around 55% silica. Andesites are in the 60 to 65% range. Rhyolites are up around 70%. I think the highest I've ever seen is 72 or 73%. You can get some ultramafic magmas. They do occur. How would you get an ultramafic magma? You have to start, you can't start with anything more ultramafic than ultramafic, okay? So in order to get an ultramafic melt from an ultramafic parent, what do you have to do? You got to melt the crap out of it. Yeah, you really got to melt a lot of it. And that just doesn't happen much today. The Earth has lost so much heat that it's rare that we have enough heat to melt that parent to that extent. But if you go back to like the Archean, there's flood basalts from 3 billion years ago when the Earth was still really hot, and they're ultramafic. They're down in the 45 to 48% range. You go to places like Upper Michigan, Keweenaw Peninsula, southern Canada, parts of Australia, they have some really neat ultramafic, really old flood basalts. Probably from a time where the Earth was a lot hotter and we could get more partial melting than we do today. Today, it's really rare to see an ultramafic eruption. Really unusual. Okay, we're going to finish today with this. Another way of looking at melting. 3 ways we can melt material. We sort of touched on this a couple of weeks ago. Remember we said that it was really difficult to get rocks hot enough to actually melt? Now, as you go down into the Earth, it gets hotter, right? But as you go down in the Earth, there's also more pressure, which makes it harder to break those bonds. So the melting points increase as well. And it's rare that your geothermal gradient is hot enough to melt anything. And that's what you're seeing with this diagram right here. So let's take a minute. If you want to draw this, okay, so on this x-axis, this is depth in kilometers. So that's how far you're going into the Earth, right? And this goes down to 500 kilometers, 300 miles, pretty deep. Upper part of the mantle. And over on the right side here, you could also scale it as pressure, because pressure increases as you go down. So it's scaled in kilobars over there. I don't think in terms of kilobars. I just think in terms of depth. But your pressure is noted there as well. And then your x-axis here is temperature. As you go from left to right, you increase the temperature. So it's kind of an upside down XY plot from what you're probably used to seeing. So temperatures go from 0 on the left, 2,500 degrees on the right. And your depth goes from the surface at the top to 500 kilometers deep, upper part of the mantle at the bottom. So you can see this sort of main line over here. All right, that red line is the geothermal gradient. And remember, the geothermal gradient is the pressure and temperature as you go down into the Earth. Okay, up here at the surface, it's cold. There's not as much, very little pressure. Near 0 in both cases. But as you go deeper, it gets hotter. And you also get more pressure. So it sort of follows that red line. Now, what you also see on this plot are 3 fields, okay? This green field is solid rock. Anytime you're in that green field, you are not hot enough to melt anything. Your pressure and temperature is not sufficient to melt anything. So you're going to have solid rock. Yeah. Well, solid in the sense that all of the atoms are bonded together in fixed positions. What you're talking about is important, but you can have solid material where all the atoms are fixed positions and it can behave brittly, like those rocks over there. If I whack those things with a rock hammer, they're going to shatter, right? If I hit them hard enough. But if you go deep enough into the mantle where it gets really hot and pressure, they will still be rocks where all of the atoms are in fixed positions. I know it sounds weird because we never see that on the Earth's surface, but if I whacked those rocks, they would dent. Though they would move, but they would move not relative to their neighbor. It's weird. Plastic rock behavior is weird stuff. But so from a phase perspective, solid liquids and gases, the atoms are in fixed positions. From a behavior standpoint, this upper part here, the upper 100 kilometers, maybe 150 kilometers, that's going to behave brittly. And then beneath it, it'll behave ductily. But it's still all solid. It's not melted. That makes sense? It's weird. Yeah, the behavior part, it is strange. Yeah, and it's strange because we have very little direct experience with things that are solid and plastic. I'll have to think of something that is solid but behaves plastically. I can't think of anything off the top of my head. Okay, so that green area is solid. Okay, it's not melted. There's no melt at all. And you can see that the geothermal gradient never gets out of there, right? So in this case, you would never get anything that melts. And that's actually how most of the Earth is, right? You don't get melt in a lot of parts of the Earth. Now you see this orange region right here? That is where you start getting partial melting. So if you were able to end up in that field over there, you're going to start melting the low temperature phases like we showed on the phase diagram. So that line that separates those two is basically the solidus. And then when you get into the yellow area, you've melted everything. So in order to get melt, we have to get into that orange region, right? So let's say you're at a point in the Earth where you are right there. Are you melted? No, you're hot, you're under pressure, you're getting pretty close, but you're not melted. There's 3 ways you can change this diagram to melt things. What could you do?
Pressure.
You could lower the pressure, right? So you could go up and intersect it that way, right? What else? Yeah, you could move this way, right? What's that? How do you do that? You're increasing the heat, right? There's a third way. You probably would do both, but there's another way to do this. What do volatiles do to this diagram? Yeah, they change the solidus. You might, instead of this being the solidus line, you might be able to get that. We actually change the rock rather than the pressure and temperature conditions. Okay? So there's basically 3 ways to melt this. Lower the pressure, increase the temperature, or change the melting point. And we're going to look at each of those here with the diagrams that come up. All we want to do is get in that partial melting area. And then we can get some magma. And the first magma we get is going to be super volatile rich. All the volatiles come off right away. And as you increase the temperature, you get more melt. So it sort of dampens out the volatiles. So the more partial melting you get, the less percentage of volatiles you end up in that melt. But the initial melt is really volatile rich. All right, any questions on that so far? We'll go through each of those now in a second. All right. So here is the first one. This is called decompression melting. You basically lower the pressure while keeping it hot, right? You're not changing the temperature. You can see that it's still, in this case, about 1200 degrees, right? You're just lowering the pressure. How would you lower the pressure? Remove rock from above it. So this is a real common mechanism for producing melt at mid-ocean ridges, because what happens at mid-ocean ridges is the crust separates, right? And as the crust separates, that crust thins out and you have less material sitting over part of your mantle. Can you think of any other way to reduce pressure? Besides plate tectonics? Go with the wild. Erosion would be a very slow way of doing it, and that is suggested for some volcanoes, that you can actually induce melting by eroding enough material off your volcano. Seems weird, right? It's like erosion is going to cause magma. Yeah. So what is sort of your biggest, what would be a big, quick erosional event? A landslide. Yeah, where you remove, a kilometer or two of volcano. That could induce melting. Now, that doesn't mean you're going to have an eruption right away. It just means you're going to initiate melting and you can start to get that. Remember, this melting can take place over thousands of years. It doesn't have to happen just like that. So that's why tectonics is a good way. Even slow erosion can do it. We have the basin and range area. How many of you have had sort of a regional geology class where you've talked about basin and range? What goes on with the basin and range? What sort of tectonics happens there? What do you remember? Is it compressional or extensional? It's actually extensional. So you're pulling the crust apart. You're making it thinner, and then some of the blocks drop down. And in a lot of the basin and range in the western US, you actually get basaltic lavas that come up right at the base of some of the ranges. You'll see a line of volcanoes that'll pop out. There's really cool basaltic volcanoes in Nevada, lots of them in Nevada, in kind of the heart of the basin and range. So in that area, it's suggested that really slow spreading tectonics is thinning the crust, lowering the pressure, inducing melting. Takes thousands of years for enough magma to pool, and eventually the conditions are right, so it erupts. Sometimes you can shed off a bunch of material in a landslide quickly, and then you can start to get melting. And some people are saying now that in polar regions where we're losing so much ice, that they're wondering if that could induce melting. You got kilometers after the last ice age. I mean, we lost a kilometer or so of ice from large parts of the planet. If that continues, maybe that would be enough to move us into the field of solid plus liquid that you see here. So the lower pressure moves this line through the solidus so that you get partial melting. You're just lowering the pressure. You're keeping the temperature the same, but you're removing overburden, is one way to think about it. So this is really good in extensional areas like mid-ocean ridges, basin and range, or where you have mass erosion either over a long time scale or short time scale, or perhaps even loss of ice. Although I don't know of a volcano that we can say is due to ice erosion.
Well, what about the retreat? Like I picture the glaciers stretching over Yellowstone and then retreating at that height.
Yellowstone did have a huge ice cap during the last few glaciations. Again, it's not, you don't know because this is just to get it to melt. How long does it take for that melt to pool, move up, go through some changes that we'll end up talking about here, and then erupt? It may be 20,000, 200,000 years for the ice caps to recede, to get enough melting, to create enough pressure to cause an eruption. So can we say for sure that the ice retreat did it? No. Is it possible? Definitely. It's just because the lag time of producing melt to producing an eruption could be so long that I don't know if we'd ever be able to say, oh yeah, ice retreat was the ultimate source of the magma for this eruption. It can't hurt. It is going to move that up towards it, right? That's just physics. And even if it hits that, is it going to be enough to cause an eruption? It's beyond what we know at this point, but those are great questions. Okay, any question on how this works, though? You guys sort of get it, right? You just remove material, you lower the pressure, you can induce melting. All right, here's what happens if we add water. Okay, you can see the geothermal gradient here. And let's say we're at this point right here. Without any volatiles, in this case, the volatile being water, here's your solidus right there. You can see that it would melt, right? But if you release water into this area, you actually change the melting point of these minerals. So that increases the size of this crystals and liquid field to include all this material in here. So just by adding water, you immediately change the melting point and induce melting. Now, this is what we think is the main mechanism at subduction zones. You have this ocean crust that sits out in the ocean for millions of years before it gets subducted, right? It's in contact with the water. It's in contact with wet sediment sitting on it. So it hydrates minerals. Think of it. At the mid-ocean ridge, you got all this nice basaltic volcanism, right? Got this pristine basalt. And then once it forms, it sits on the ocean floor for a couple million years, and all these minerals get hydrated. You get minerals like serpentine that have lots of water in it. And then that hydrous slab of basalt descends into the upper mantle. And it gets to a depth where it's hot enough that it will drive that water out of those minerals into the surrounding rock. And that immediately will lower the melting point. So, for a lot of years, if you took, back when I was a student, you'd hear that, the reason we have so many volcanoes at subduction zones is because of friction. You got the two plates rubbing together, and it's that extra heat from friction. That's what I was taught. That doesn't happen. There's not that much friction down there to create heat. What you are doing, though, is you're descending a slab with hydrous minerals to a depth that you're driving the water out. And then once the water is free, that lowers the melting point. Now, how that does that, that's for the chemists to tell me, and I'm not going to get into that in here. Just suffice to say, you add water to these really hot rocks in the upper mantle, you change the melting point. You make it easier. Actually, what happens is the water breaks some of the silica bonds, the silicon to oxygen bonds, starts to break some of those so that you don't need as much energy to start to melt things. Okay, so melting lowers, or water lowers the melting point of these rocks, mostly in subduction zones. Heating. Now, this is the tough one. Where are we going to get some heat from? We talked about the geothermal gradient not being enough. Maybe we can add some radioactivity. It's probably not enough. How are we going to get heat in here? This is the hard one to explain. I don't expect you to come up with an answer because it took a long time for petrologists to sort of figure this out. But they figured it out by looking at some of the melts that came up to the surface. So you can go to areas like Yellowstone and look at these beautiful silicic rhyolites. And they will have inclusions of basalt in them, little clumps of basalt that haven't been altered at all. So the suggestion is that this was an injection of some basaltic magma that had formed deep down. Remember how I said earlier that most magma that forms rises to a point and then doesn't go anywhere because the density is the same all around it? So there's lots of magma sitting down in the earth that never erupts. But every once in a while, you can move that magma into an area and induce melting from it. So it's a crass term, but I've heard this a lot of times. They call it a basaltic enema. You sort of squirt basalt into a place where it hasn't been before. And that basalt obviously is really hot and has a lot of excess heat, especially as it starts to cool. Because what happens during cooling and during crystal formation? Remember all that latent heat we talked about? That gets liberated to the environment. And maybe that's enough to cause melting. So the heat comes in through another liquid, basically. And that liquid being some magma that's down there. This is probably pretty rare, but there is evidence for it. And I'll show you a slide coming up here right now. I'll let you finish your notes though then we'll finish with that. So here are some photos of some basalt inclusions in some more silicic, mostly andesites, okay? So up here, you can see this is the main lava. It's andesite, but you see lots of little basalt clumps. Here's some andesite here, and here's a basalt clump. Really common. In fact, some of it's even really vesicular. So not only is it releasing heat, it's also releasing some volatiles. What do we say volatiles do to the melting point? It lowers it. So it's sort of a doubly effective way. You bring in some heat and you bring in some volatiles. So you have more heat and you have lower boiling point or melting points. So is it common? You see these things. Is it enough to create lots of magma? I don't know. Probably create some though. Most of your melting though in mid-ocean ridge areas are going to be from decompression melting. Most of the magma that you form in subduction zone areas are going to be from pumping volatiles into the surrounding rocks and lowering the melting point. When you can't explain your volcano one of those two ways, then geologists start looking for this. You know, maybe there was some heat and volatile source that was injected into the area. Yeah.
So when this new basalt comes in,
yeah,
that basalt does not melt. The andesitic melts.
Yeah, the basalt's already melted,
Okay.
and in fact, the basalt might cool. And as it cools, it releases heat and volatiles, and then melts the surrounding rock that it's in.
I'm assuming that these basalts, they were the first to form.
Yeah. Okay, so take away those three things: decompression, changing the melting point by adding volatiles, and adding heat with maybe some basalt that's sitting around at depth. So that's kind of the takeaway from the last part. Takeaway from the beginning part is that your melts are always more silicic and different than your parent rocks. Start with a mantle parent, you end up with basalt. Start with a crust from the ocean and you end up with andesite. Start with crust from the continent and you can end up with rhyolite because you're only partially melting these things. Does that make sense? Okay. That's enough for a day. All right. See you guys all next week.